So it's very often the case that either the region that we're describing in xy space is better described in non-rectangular coordinates than it is in rectangular coordinates, or that the function we're trying to integrate is better described, more easily described in non-rectangular coordinates than in rectangular coordinates. And so our job now is to sort of figure out, if I want to make life easier on myself by changing my coordinate system, by replacing rectangular xy coordinates with some other way of measuring coordinates on the xy plane, then how do I have to change my approach to an integral? And also, how do I have to change my approach to tape measurement of the region that we're trying to describe? And so what we're going to do is kind of a two-step process here. We're going to do a quick refresher about how polar coordinates on the xy plane work. How do we convert back and forth between both coordinates of points and equations that describe curves in xy space, back and forth to r theta instead of xy. And then, most importantly, what has to change when we change the coordinates on the xy plane from xy into r theta? How does our approach to double integrals have to change? And the motivation behind this is that secretly, in single variable calculus, when we learned u substitution, secretly what we were doing is choosing a new coordinate system on the real line. Right? If my original coordinate is called x, and then I want to replace x by u in my integral, then that u is like a new coordinate. And when I replace dx by du in the process of doing a u substitution, if you'll remember, there was this factor that we had to multiply by or divide by. We end up dividing by, I think, the derivative of u with respect to x, right? When I swap out a dx for a du, we also have to, we end up getting this additional factor that's multiplied by, that is related to the derivative of one of those coordinates with respect to the other. And so, as you might expect, the same thing is going to happen here when we transfer from xy into r theta coordinates, that we'll have to multiply. There's going to be some factor that we multiply by that is going to be related to the derivatives of the relationships between r theta and xy. But there's 4 of those relationships, right? R depends on x and y, theta depends on x and y, and so there are sort of, each of those coordinate functions has 2 partial derivatives associated with it. So how do we assimilate all those partial derivatives together? What should I be multiplying by when we translate coordinates from xy into r theta? That factor that we multiply by, just by way of terminology, is called a Jacobian. Jacobian just tells us what is the amount by which area changes when I change coordinate systems from one to the other. So let's get started just by quickly refreshing what polar coordinates are and how they work. So in rectangular coordinates, we use an x and a y to measure the distance of a point respectively from the y-axis and from the x-axis. Right? It's called rectangular because the equations x equals constant and y equals constant define for us vertical and horizontal lines respectively. And so they will sort of mark off, if we use constant limits on x and y, they're going to mark off a rectangle inside of xy space. Meanwhile, r and theta, instead of using 2 lengths to measure coordinates like x and y do, we use a length and an angle. And a length and an angle can uniquely determine a point within xy space in a lot of different ways, but the way in which we call polar coordinates is that we say that that length is the distance of my point from the origin. And that's the coordinate that we call r. So r is just the length of the hypotenuse of this right triangle, where x and y are the 2 legs, or equivalently, it's the distance of my point x comma y from the origin 0, 0. And then theta, our angular coordinate, is the counterclockwise angle made by this radius, measured from the positive x-axis. And so in order to describe the entire xy plane, it's sufficient for me to only consider non-negative values of r. So I only need to make my radius either 0 or something positive. We're never forced to make this radius a negative number. If I made this radius a negative number, probably I would be trying to think about multiplying this vector by -1, and so it's the opposite direction. And so instead of using a negative radius to describe opposite direction, we just use a different angle to describe opposite direction. So for us, r is going to range from 0 to infinity. Similarly, our angular direction, we can describe the entire xy plane by letting my angle vary just from 0 to 2 pi. Right? That's going to give me the entire xy plane, because every point in the xy plane makes an angle with the positive x-axis measured counterclockwise that is between 0 and 2 pi. Of course, we could choose really any other 2 pi width range for my angular variable, but 0 to 2 pi is the most convenient because we get a 0 in there that we can use to help us to orient ourselves. And so with those definitions, we have these conversion formulas that get us from rectangular to polar and vice versa. And those just come from this right triangle that we have up here, just applying right triangle trigonometry to this. So the Pythagoras Theorem tells me that r is going to be the square root of the sum of x squared with y squared. And also that theta, this angle, is going to be related to the rectangular coordinates by the fact that the tangent of theta is going to be the opposite side, which is y, divided by the adjacent side, which is x. So if we know rectangular coordinates and we want polar coordinates, that set of conversions will help us. Right? R is the square root of the sum of the squares of x and y, and theta is the arctangent of the ratio y over x. As long as x is not equal to 0, if x is equal to 0, that means that we must be on the y-axis, and so the angle theta is either going to be pi over 2 or it's going to be 3 pi over 2, depending on if we're on the positive or the negative y-axis. If we want to go the other direction, then we want to solve for x and y in terms of r and theta. That ends up being a little bit easier, a little bit more straightforward, because there, in order to relate x to r, for example, I'll use the cosine of theta, the adjacent divided by the hypotenuse. And so the adjacent side is equal to the hypotenuse times the cosine of the angle. So x is equal to r times the cosine of theta. Analogously, since the sine of theta is y divided by r, opposite over hypotenuse, that means that the opposite y is equal to the hypotenuse r times the sine of the angle theta. So x is equal to r cosine theta, y is equal to r sine theta is a conversion if I know the polar coordinates and I want to get to rectangular coordinates instead. So I have a Desmos worksheet to help us with this next activity, just to create your visuals. But I do encourage you to, instead of jumping directly to the Desmos where it asks you to sort of think first about what shape this curve has before you use technology, to do that part, just to reinforce the intuition. But in this activity, you're going to be plotting some equations that relate r and theta together and seeing what they look like as curves, perhaps, in the xy plane. And then also describing regions in the xy plane by using bounds on the variables r and theta. So that's going to look more like tape measuring. And so the Desmos worksheet that I have to help us out is just an extension of the one that we started using yesterday. It has the type 1 region tool in it, it has the type 2 region tool, but it also has a polar coordinate tool in here that you can use as well, where we're bounding r in between two functions of theta, and then bounding theta sort of as we will. And so to use this one, if you want to change your bounds on theta, you actually have to go into this menu to change them. I just didn't put in a little tool to change these. So if I want to use a different range of theta values, then I have to adjust those in here instead. So I will let you go ahead and get started on 11.5.2. I think maybe let's do parts A, B, and C first, and then we'll come back and debrief, and then we'll move on to D, E, and F, because those parts are going to be more about tape measurement. So the curve r equals 1, so it has a fixed value of the radius, but the angle can be anything, gives us a circle, right? And the radius of that circle is that constant value of r. It's all the points that are a distance of 1 away from the origin. That gives me exactly the unit circle in the xy plane. Theta equals 1, meanwhile, is going to describe all of the points that make an angle of 1 radian with the positive x-axis, measured counterclockwise. So it gives me a line, actually it gives me a ray starting from the origin and going out to infinity, and that ray makes an angle of 1 radian with the positive x-axis. As when you were doing this problem, you mentioned that this line would have a slope equal to the tangent of 1, which I agree with. So that is another way to think about what tangent means geometrically. Tangent just means slope. The tangent of the angle is just the slope of this line. But we only get this ray. We don't get the full infinite line because the points that are in the third quadrant would make an angle of 1 plus pi radians with the positive x-axis rather than 1. And then we have a curve r equals theta. Because the radius is increasing as we increase the angle, it traces out this linear spiral as we go outwards. So now we'll do parts D and E that just give us an opportunity to do some tape measuring. And so if I put an inequality on my r, or an inequality on both my r and theta, we'll figure out what kinds of regions that will describe inside of the xy plane. And so you can use, again, this tool to put your inner function and your outer function in here to be whatever you'd like, and then change the bounds on theta using these sliders, and you'll have a visualization of what that region looks like.